Hello and welcome to another episode of Naturally Curious. This is a show where I pick the brain of different cool people every episode. My name is Clayton Law and my guest today is physics professor Rayf Shiell. How are you doing today?
Good, thank you. How are you?
I'm good. Let's just jump right from the beginning. Did you like science when you were a kid?
I did. I liked asking questions. And for me, I think that is what science is at its core. So I was a kid who tended to always ask the question why, and I've always wondered why, but that applies almost as much to the natural world, which is what physics is, as to what I observe around me. So I sense maybe I was always a curious kid.
But you didn't know that you liked science then when you were a kid.
So I was I was just curious about essentially everything that I observed. And then through my schooling, I found that I was able to answer the questions more easily about the physical world. And I think that's then how I became more interested in science.
Why did you choose physics? Why do you like physics more than other science?
So I think that physics I see as something of a foundational base for all the other sciences. So I also am interested in biology. In fact, I've also spent many years working in chemistry departments. My training is, I suppose, that of a chemical physicist. So I'm on the boundary or interdisciplinary between chemistry and physics. But I think that where my natural curiosity leads me is to physics, which enables me then to understand both the micro and the macro of fairly simple systems, and then apply it subsequently to more complicated examples that you would see in chemistry or biology.
When did you know you want to be a physics professor? Or did you want to actually you still want to be a football player or something?
Yes. For me, I think the sport was rowing, but
yes, of course. I actually have that on my notes.
Okay. So yes, I think that what I find is that science and physics in particular is a subject where when you first ask a question, it then opens up another set of questions, which are, and it sounds surprising, but even more interesting than the first question you started with, and even more, and with even greater ramifications. And so then you answer that second set of questions, and that sort of gets you from sort of high school, if you sense, to maybe the second year of university. And then you've got a third set of questions that you've opened up. So it's like one door leading into another room, And every time you pass into a different room, it's a richer, really more intellectually elegant experience. And so in a sense, I fell into being a physics professor because that's a natural evolution from the first room to the second to the third.
Let's move forward in time a little bit. After you have graduated from Oxford,
yes,
you went to do your PhD in Newcastle.
Yep.
And after that, you decided to go to Canada.
Yes.
Why?
So I suppose for the same reason that I moved in the first place from Oxford to Newcastle, but on a larger scale, which is that I feel that different experiences help enormously with one's learning. And so when I was at Oxford, it was a very vibrant and it's an amazingly stimulating place to be. And then the offer came for me to do graduate studies there, and I thought, well, it'd be nice to see what other experiences there are and what other environments there are. And with different environments, I think you can acquire and learn new, almost intangible skills and benefits, acquire new benefits. So I looked outside of Oxford for that, and that's then why I went to Newcastle. So my graduate work was at Newcastle. I finished that, or as I was finishing it, I'm thinking, well, I'm still in. To use this analogy from before, I'm still in one of these rather delightfully interesting rooms of academic endeavor, and so I'd like to continue in that realm. And again, I'd like to experience a different environment. I'd like to see science being done in a different environment. And so I was at a conference. In fact, the conference was on Vancouver Island. And there I met a professor who had just given a talk, who had actually done some really very interesting work, and saw some of the delightful aspects of atoms and molecules. And so, as happens at academic conferences, you just talk to the profs, you just talk to people, and actually, he offered me a job to come and work with him at Waterloo, and that was in the chemistry department. So, in the field of laser chemistry. So, of course, there was paperwork, etc. But that then sort of scratched my itch to do science in yet a different environment again.
What did you do in Waterloo? Were you teaching or?
So I was. So the position itself is called a postdoctoral research fellow, meaning that it's after the PhD, which is the doctoral aspect, but before a faculty position. So essentially, it's not dissimilar to an internship that you may have heard of from the medical community. And what it involved is really principally research, but I was fortunate to also have the opportunity to teach courses at Waterloo as well. So because I'm on the border between chemistry and physics in terms of my interests and my expertise, my research was laser chemistry. So using light to manipulate, to create, to study, investigate large atoms and molecules. And my teaching was really in the realm of physical chemistry. So that would be in quantum chemistry and in optical techniques.
I couldn't quite track down the timeline properly when I was researching. Did you bounce around between Waterloo and Queens?
No. So maybe that link that you're alluding to there is that since I arrived at Trent, I have been an adjunct professor at Queen's, and so able to supervise, and some of my graduate students have enrolled and graduated through what's called the Trent Queen's program, which is a joint program, but provides the student with a Queen's degree. And in order to do that, an adjunct professor assignment is required for the supervisor. So maybe that is how the Queen's link appeared on my webpage.
So the proper timeline will be: you graduated in Oxford, went to Newcastle, went to Waterloo, and then you hang around there for a couple of years. Then you went to Trent.
There's one step in the middle. So Waterloo was actually a 4-year position, and then I'm sort of the next set of career-based rooms or doors that you walk through is indeed application for a faculty position, and so the faculty position I first got was actually back in the UK, in the University of Sussex, where for about 4 years again I was building a research lab and conducting teaching. And after that point, then that was a faculty position, but what is termed a non-tenure track faculty position. So it didn't have permanency associated with it. It enabled you to certainly apply for grants and get grant money, publish, to teach, to get more experience. But then it wasn't a permanent position where you could have a long-term research plan. And so I moved then from Sussex to Trent.
How could you have gotten like a permanent faculty tenureship in Sussex? Like, do you apply or do they offer?
So the way this works is that individual universities, and there are something like 60 odd, maybe more now in the UK. There's about 50 to 60 here in Canada. So individual universities each year make a decision over where they will and in which subject field they will be hiring. And so to get a faculty position requires that your expertise and your interest allies with that year's round of positions. And so when I was applying sort of towards the end of this non-permanent position, I was sort of looking in various places, and certainly my wife at the time was very keen to come back to Canada, and so we looked in Canada again, and Trent had that position available, so I applied to Trent, and they were hiring within the field of physics, and they were open as to which subfield within physics was hired. So therefore, in that sense, it was in a sense a peg in a hole problem that got fixed.
So usually I would try to understand the concept a little bit, like do some research on whatever concept that I want to talk to the professor. But I just can't understand quantum mechanics. I can't even grasp a tiny bit of quantum mechanics. Like, so you got some small things light years away, two small things light years away, and they react to each other instantaneously. I read something like this, and the Wikipedia page was unreadable. But can you just quickly I don't like to ask professor to do this, but can you dumb down a little bit of what quantum mechanics is?
So I can certainly try. I acknowledge, as you've alluded to, that there's often within a single sentence of science, within of scholarship in general, there's a lot of information behind the scenes, behind the curtains, that has led to that single sentence or that single fact, if you wish to use that term. So certainly quantum mechanics has now 100 years or so of very dedicated research behind it, and the aspect that you're alluding to is this rather odd sense that there is this spooky action at a distance, and so the question there is sort of what is that and what's meant by it. So one of the remarkable aspects of quantum mechanics is that, unlike a classical die that you would throw if you're playing Monopoly, which when you throw it either is in a 1 or a 2 or a 3 or a 4 or a 5, 6 or a 7 when you throw it, small objects can exist in what is termed a superposition of two or more states. And so you could think of it as throwing a die, and the die happens to be both in a 1 and a 2. Or perhaps if it's a coin, it's both a heads and a tails. And so when you come to measure that, when you say, hey, what is the value on that die? Or when you say, what was the face on that coin? Then that superposition, or you could call it a mixture, collapses to one of those, one of the possible answers. So a nice example might actually be socks. If I was to think of a sock that I pull out my drawer, it's typically either red or green or blue or black, right? Because I've got some colorful socks. Now, at a small scale, particles can exist as if they are a sock that is both red and green. So that means then that it's in this mixture of red and green. Now, if I pull two socks out my drawer, and I do it in such a way that I know one of them's red and one of them's green. Actually, I'll rephrase that. If I pull two socks out my drawer, and I just happen to know that of the two, there's a red sock and a green sock, it's possible for both of them to be in this mixture of red and green. you to take both those socks, separate them by light years, and then look at them, and only then look at them. And so until you look at them, the socks are both in a mixture of red and green. But the minute or second that you look at one of the socks and you say, wow, look, it's red, then the other sock instantly must be green. And this is a term called entanglement in science. It has a lot of powerful ramifications. It not only is the science behind why atoms and molecules behave the way they do, why the periodic table is the way it is, but it's also enables fields such as quantum computing and quantum processing to become realized. So now I'll try and cut then to the explanatory sentence that you were looking for 5 minutes ago. And what I would say then is that I think what you are what you are curiously asking about is the sense, the very real and observed sense, that if you take two particles that have a common history and are therefore, the term is entangled, it is quite remarkable that you can take one of them to one side of the universe and the other one to the other side of the universe, and then and only then measure which state or which property one of them is in, and the other one, even though it's many, many light years away, will instantly have the other, if you like, the complementary property. So in the sock analogy, perhaps, I pull two socks out my drawer. I don't look at them. One of them I put in a box. The other one I put in a box. I send each of those boxes to the far side of the universe. And then when I open one of the boxes, the first one is green. And that means to say I can guarantee that the other one will be opened and the other sock will be red.
How is Schrodinger's cat? I can see some similarity between the socks example and Schrodinger's cat, but Schrodinger's cat just doesn't feel very understandable.
Yes, so I suppose at its core is the sense that particles can be waves, i.e. exhibit wave-like properties. And so it's possible then to have properties that are not uniquely set. So Schrodinger's cat is the analogy, and Schrodinger, I don't even know if he had a cat, but he used this as what's called a Gedanken or thought experiment. He said, let's pretend that our electron is this thing called a cat, is this cat, and I'll put it in a box, and I'm going to create the option that the cat could be 50% chance it's alive and 50% chance that it's dead. And he sort of thought about that by saying, well, let's put a little bit of radioactivity into the box too that might make a vial of poison be released if the nucleus decays radioactively, and then the cat happens to die. Now, he never did this with a cat. This is purely a thought experiment. So the cat itself is you can use the term mixture. It actually has a slightly different meaning in physics. So officially the term would be superposition. But let's use the term mixture for now. So the cat is in a mixture of being alive and dead in this model. That is analogous to the sock that is in a mixture of being red and green. So it is both red and green with a 50% likelihood of each. When you look at it, you then observe either a red sock or a green sock. And that is really the foundation of much of the philosophy, or the questions that stem from that are the foundation of the philosophy of quantum mechanics, and what is real and what is realism. And so what we see, to bring back the analogy to the rooms that I spoke about earlier, is that by talking about the states that quantum systems can be in, we've now entered really one of two rooms, one of which is philosophically saying, okay, that seems weird. Why is that true? And what is reality? And a second room, which is, wow, that seems weird. What can we do with it? And can we check that it is indeed what we observe from the world? The first of those rooms really enters into a field called physics of, or the philosophy of physics. And the second is really what physicists spend a lot of their time doing, which is acknowledging the unusual non-intuitive aspect of quantum mechanics, but then using it and applying it. So again, each room leads to another room, and so what we tend to do as physicists is recognize that atoms, molecules, electrons, basically small proteins act like this, and then we try to use that for beneficial means. But it does also, on the side, we recognize that there's a big room called, well, what is realism? And I think Richard Feynman was he was a Nobel laureate from a very accomplished physicist in the 20th century, and essentially he said that he feels that nobody truly understands quantum mechanics, and he was an expert in quantum mechanics. So what I think he's alluding to there is that your question is a very well posed question. It opens up many subsidiary lines of inquiry, and we always end up with more questions than we do answers. And as a scholar, the question that one has to ask oneself is, okay, at what point do I which area am I going to do research in? Which area am I going to focus in? Recognizing that there's a lot of uncharted territory that remains.
Another one of your, like you mentioned earlier, one of your research interests is in laser. So it seems like the 2018 Nobel Prize, Nobel Physics Prize, the thing that they were doing is right up your alley.
Yes, in fact, the award, at least a substantial fraction of the award for the Physics Nobel Prize in 2018 was for a technique called chirped pulse amplification, awarded to Donna Strickland at Waterloo and Gerhard Murrow at Rochester. He may have been, they may have been in Michigan as well. So I may have the actual affiliation incorrect there. But Donna Strickland indeed is a remarkable physicist at the University of Waterloo, and I overlapped with her when I was there. And so this was her graduate work in the mid-'80s, where the technique was really quite a clever one of trying to increase the power of lasers' pulses without destroying the laser itself, as you pump more and more power into the laser, into the laser light. So chirped pulse amplification is a technique effectively to do that.
So it sounds like it is, I'm sure it is not simple, the work behind it, but it is, I intuitively understand what it means. So is it more compared to other Nobel like Physics Prize? Is it more like a simpler thing that was awarded?
The answer, I think, is that the challenge is, in this particular case, actually getting the experiment to work. And what your question, I think, gets to the root of, which is a very good one, is that there are different challenges with every field. Supplies within academia as well as my observations within physics and the natural sciences. So the challenge often with with experimental work, which this absolutely is perhaps articulated best as thinking of juggling, where the task is first that, like all research, you don't know it's going to work. So you have a hypothesis that you think, well, if we do this, and we do this, and this happens, and we do this, and we do this step here, then, wow, we might get this really powerful laser beam, for example. But it may not happen. So all research is essentially a leap into the unknown. And so what it involves then is a lot of understanding of everything that's gone before you, the technical aspects, what type of crystals, in this case the laser crystals that are used by Donna Strickland and Gerhard Moreau. All the optics, which means all the lenses, all the attributes of the light, the way in which its wavelength, its intensity, its polarization, which is another property that light can have, all have to be aligned in such a way. In the same sense, I suppose, as you'd say that the stars have to align for an experiment to work. But in this case, they all have to be engineered to be aligned. So I would say that this chirp pulse amplification technique is definitely deserving of a Nobel Prize. It can be perhaps described with a diagram in a way that's more intuitive to us, but the challenge of getting it to work is as great and deserving of a Nobel Prize as all the others. And just to sort of circle back to the juggler analogy, essentially it requires for the first time, it required in the mid-80s for the first time in history for these two researchers to enable ball number 1 to be in the air, so the intensity is the correct value, while ball number 2 is in the air, the polarization is the correct value, while ball number 3 is in the air, the crystals have the right temperature, while ball number 4 is in the air, the current through the various power supplies are what they have to be, etc., etc. And if any one of those balls falls down onto the ground, then the experiment cannot work.
Would you get laser surgery?
Would I get laser surgery?
Just so the audience know, Rayf wear glasses.
Right. Yes. Yes. I am indeed quite nearsighted, as an increasing number of people are as time progresses. I actually have fairly thin corneas, and so it's not appropriate for reshaping the cornea, which is what laser surgery actually involves. So laser surgery has various types. One that you may have heard of is LASIK. Another one is PRK, and they have different approaches. But in all cases, it involves reshaping the cornea, which is the very front of your eye. It's the transparent window that holds all the fluid inside the eye and maintains the eye's spherical shape while allowing light to travel into the eye. And so reshaping involves removing some of that cornea, just sort of basically scraping away, but thankfully not with any sandpaper or anything, but in fact just using indeed laser light. And chirp pulse amplification, which we've just been speaking about, is indeed used to ensure that the laser has sufficient power in a very small amount of time that it can take away, it can ablate is the term, some material from the cornea without actually without causing widespread damage. So it targets the cornea, but the cornea has to be thick enough for that material to be removed.
So you can't do it.
So that's correct.
Yes. When I was a kid, I used to think that I'm someone special because I had a lot of deja vu, and I didn't know how to explain it to my parents. So I just kind of didn't say anything, and I just thought like I must have superpower. And turns out everybody have deja vu. And then there's another thing that also makes me think that I'm someone special is I have after image. But turns out everybody has after image. When I used to do as a kid is that I would close my eyes and I will press on my eyelid, and then there like weird patterns will show up in my, like I would see weird patterns. What does that, how that happens?
So the eye is a fascinating object because it connects physics to biology through many paths, and so it is. So perception, visual perception itself, is truly an interdisciplinary subject. So the after image that you referred to, where, for example, you stare at an object for a while, and an example might be a fairly colourful object, perhaps a fairly simple colourful object, perhaps a very simple flag that's colourful, and you stare at that flag for a while, for 20 seconds or so. And then when you look at a blank sheet of paper, what you'd see is on the paper, it's faint, but you do typically see this, is you would see the complementary colors of that flag. So I suppose if, for example, you have the Swedish flag, which is blue and yellow, for example, with then what you would see is where there was the blue, you'd see some brightish yellow on the white sheet of paper that you're looking at. So that's an example of what's called a negative afterimage. So there you've actually got the latency, or the cones, which are receptors in the retina, have essentially been triggered in such a way that when you then close your eyes, or rather when you then look away at a white sheet of paper, the nerve impulses from the retina still continue to fire in such a way that there's this impression that the colors have changed. Now that's really it's a neurological phenomenon. In other words, it's to do with the cells and the nerves, and so I imagine, but I don't know, that the pushing on your eyes, which probably wouldn't be broadly recommended, can indeed have the same effect. And in fact, you aren't alone in trying to push your eyes. But again, I wouldn't recommend it. I mean, Newton once tried to sort of push his eyes so much that he almost caused himself to go blind. So I think you want to be careful. And part of science is thinking before you touch anything.
I don't do that anymore. I was just a kid that just when I couldn't sleep, I just like, let's try for fun.
Yeah, absolutely. Yeah. I mean, the body has a degree of resilience, which is great. But as an experimental scientist, I do teach my students very much that before you engage in a particular task, you think about it to make sure that it's highly probable that everything will be okay.
So the pressing, like the thing that I said, like press on my eyes and I see a weird pattern, that is not after image. That's something else.
That's correct. That's not an after image. Exactly.
Okay.
That's right. But you would, to explain that, would require unpacking whether. So I don't know if this is with your eyes open or with your eyes closed. That's right. With your eyes closed. That's right. So at some level, there's a stimulation of the nerves that then get the impression that you're getting some signal to your eyes. When you do blink, of course, there's no, or when you have your eyes closed, there's no light entering the retina, hitting the retina. So to see anything when you're doing that is, it could be packaged as a neurological thing, a neurological phenomenon, and so that would require unpacking that part of vision. The latency of your eye actually is partly, I mean, we're thankful about it, because every time you blink, you don't suddenly see blackness. When you look around, when I ask you to admire a painting, for example, at an art gallery, you might be looking at this painting for 30 seconds and saying, wow, it's really quite a beautiful painting. And at no point do you say to me, well, it would have been really good if it didn't constantly go black every time that I blinked. And so there is an example where the latency of the cones and of your eye, and also your brain, which actually connects to the eye in such a way that it de-emphasizes signals that come when you blink, together work in such a way that you don't notice blinking. So you have to try to notice you're blinking.
I'm noticing now because you were talking about it. So yeah, you can't count how many times I've blinked unless you try to count.
Exactly. That's right. Yes.
So there's one camera that was, invented, that could film 10 trillion frames per second. So it can actually film light traveling frame by frame. What does that mean for studying light? So in the same way, actually, that perhaps a nice analogy that ties in with the origin of photography is that there was a big debate for many I'm going to guess mid 19th century, as to how horses actually ran, because we could see horses walking, and we can visualize, as humans, we can see their legs as they walk,
But there was a debate over how horses ran, whether they run with two legs reaching out in front of them and two legs back at the same time, or if they run with a different gait. So the way that was actually resolved was through a camera, because horses move too fast for us as humans to be able to see, partly due to the latency effect of the retina. Move too fast, their legs move too fast for us to actually determine how it was that they were running. So essentially, cameras have achieved a lot in terms of finding out, in terms of information gathering, in terms of understanding nature. And so, of course, a horse travels, I'm going to sort of estimate maybe about, maybe 40 kilometers an hour, maybe 50 kilometers an hour, that type of speed. And light travels, 300 million meters per second, but still it's many thousands of times faster than a horse. And so, essentially in a foot, they've traveled a foot in a billionth of a second. So therefore, what we learn by slowing things down frame by frame can inform us about how light interacts with materials. So as it passes through glass, what actually happens to that glass? How much does the glass distort, for example? How does the light beam actually? How does the light beam or light pulse in this case behave as it starts to reflect off that glass? And glass itself is a fairly inert material, but I'm reminded of Michael Faraday's reply when he was asked, this may be an apocryphal story, but I think the message is a good one, when he was asked by the King of England, well, you've discovered this thing called electricity, but what use is it? And his reply was, I do not know, sire, but what use is a newborn baby? And in the same sense, I think a lot of science has progressed in what we have today, which is remarkable levels of technology, information and predictions, based upon taking a new tool and applying it and letting nature almost be the guide. So with a camera that can image light frame by frame as it passes across the room, as it connects, as it reflects, as it interacts with glass, but not just glass, maybe with cells, maybe with tendons, maybe with biological materials, then who knows where it can lead. But essentially, almost every major advance in science has taken place because of open-minded playing.
There's a question that I want to ask, but I don't know who to ask, but I feel like you can probably answer this question. So ever since I have the understanding of how energy is generated, ever since I understand why people burn fossil fuel, how that generates energy, how wind turbine works, I have the idea that we should harness the power generated from an earthquake. Let's ignore the engineering part. Is it theoretically possible to harness power from an earthquake?
So I think so. I think it's entirely theoretically possible, and you are right that any application, any human application, requires both a scientific foundation plus the technical and technological expertise and development. So it is perfectly possible to store energy from vibrations, from sound, and an earthquake has, as you say, a significant amount of energy associated with it, and so in the same sense that tidal energy can be stored, then it is theoretically possible. There's nothing preventing us imagining a scenario under which there happens to be an an earthquake, we have generators, basically vibration-based generators, and they store this energy. Ultimately, I think one of the really powerful and beautiful and elegant aspects of science is that for it to work, it requires an understanding of the micro and the macro. And so there's the theoretical principle, and then there's the theory of the experiment. In other words, okay, so now when I put in real wires and real generators and I place them at real places, of course, we don't know, we can't predict yet. And one of the advances that I'm looking forward to is being able to predict, is for us as humans to be able to predict earthquakes much more reliably. But when when you fold all those facts into the problem, does it become a viable option is then a very an important but different question. And so at the moment, I sense that the unpredictability is such that we wouldn't be pursuing that as an avenue for energy generation. Geothermal, of course, which uses the latent heat, the embedded heat within the Earth's crust, is a technology that is being rolled out at the moment.
Are you good with periodic table? I see you have a periodic table over there.
There is a periodic table behind me. Yep.
How do you pronounce the element with atomic number 13?
Aluminum is how I now pronounce it. Aluminium is how it used to be pronounced in Britain and still is by people who have not yet encapsulated the spelling that is now uniform, which is aluminum. So the spelling does not have the extra I. And I can't recall precisely when that happened, but I'm going to estimate maybe about 20 years ago. And actually a similar anecdote would be the element sulfur, which for a long time in Britain and other places was spelt with PH, S-U-L, P-H-U-R. But indeed, we need to have some standardization in order to effectively communicate. And so it was subsequently determined that it would be spelt with an F, S-U-L, F-U-R. And there are some people that, just out of habit still use the PH. And so likewise with aluminium, I'm fairly sure that it is now officially spelt without the extra I that would give it that phonetic sound. And so aluminum is indeed the way that I spell it, or pronounce it rather, both because I'm in North America and because I believe that is what UPAC, which is the committee that determines these things, has decided, and it's certainly functional.
When was the sulfur thing changed? When was that?
So I don't recall, but there are of course countless pieces of trivia in any subject, but I imagine again it was around 20 years ago, but it could be. I mean, you could find out.
Because I never noticed that it used to be PH. I just know it's spelled with an F.
That's right.
So it must be before.
Well, it was either before your time or it was subsequently to you studying it, but here it was F, and in some other countries, for example in the UK, it was PH. I mean, last week, for example, the kilogram was redefined in a particular way, and you may not have encountered that just because it doesn't affect you sort of in your everyday life.
Mm-hmm. Like 1 kilogram of things is still going to be 1 kilogram, like for me.
Exactly.
Like
yes,
when I go get
right.
groceries.
That's right. Exactly. Yeah. Yes. To any level of accuracy that you measure it will indeed stay the same. Of course, I mean, the GPS system that we use in our satellites requires the second to be very, very precisely defined. Even though the second hasn't changed to you and I, from its sort of definition in antiquity, that doesn't mean to say that by changing these things we can't enable more technologies.
So I have this one little argument it's not really an argument, discussion with my friends. It's about is water wet? From a physicist's perspective, is water wet?
So in essence, I would say that it depends upon what substance you're putting it on. What water is conglomeration of H2O molecules, which through their interactions, which mean the way that the electrons behave inside those molecules, enable these molecules to attract and stick to some other substances. The term I suppose we could use is hydrophobic for those substances that it sticks to. So your hair, when you come out the shower as an example, where water sticks to your hair, it doesn't dry. Your hair takes time to dry. The term that we use for that particular form of connecting from water to your substance is hydrogen bonding. So water certainly seems wet to your hair in the sense that you put it on your hair and it sort of doesn't, and it doesn't just evaporate away. But there are other substances that it doesn't stick to as much. So it hinges upon, and this is why I think at its core, we need to be able to understand the small and the large scale. It hinges upon the way the electrons in the water molecule behave when they encounter the electrons in, for example, Teflon, or for example, your hair. So whether water is wet or not, I would say, and I'm not a fluid scientist, but what I would say is my interpretation of answering that question would be it depends what material you're considering.
Okay, I'm sure I will ask this question again to other like maybe philosophers. Like, is water wet in philosophy? I'm sure I will probably
Absolutely.
ask. Sometimes when I can't fall asleep, I think of things. One of the things that I think about is, like, I get frustrated to think that my physical body can only do so much. It's like I can never experience fourth dimensional space. I can never see past red and violet, and I can never travel faster than speed of light. That kind of thing. I'm sure you have encountered things that are very abstract that you physically cannot experience. Do you get frustrated because of it sometimes, maybe?
That's an intriguing question. I think so. One answer that I have to that question would be that ultimately the world in which we live, and by that I mean also the universe in which we live, it remarkably, and there's no reason this has to be true, and this now enters into philosophy of science, but remarkably it obeys a very consistent set of rules. So one answer to your question is the limitations that your body has are a reassuring confirmation that the universe obeys a consistent set of axioms or rules or base principles. So if it was the case that suddenly one person could sort of break the rules of science, it certainly would at first be quite exciting, but then it would also mean that it actually maybe there isn't a whole set of rules applying to the universe, and therefore basically all bets would be off for any prediction made from that point onwards. Will the sun rise tomorrow? We don't know. Would the Earth be rotating in 5 minutes' time? We don't know. So one answer to allay a concern about limitations would be, well, isn't nature quite powerful and quite influential that it sets the rules, not you? So you may wish that you could jump to the top of a 40th story building, but science won't let you. And if you could, then all bets would be off from that point forward, for good or for ill. So I think my first answer would be actually it can be kind of reassuring that at least there's this consistent set of principles that the universe follows, and that includes, for example, your eye having a particular material in front of it, the cornea, which then limits the amount of light that can get through in such a way that you can't see beyond red and you can't see beyond violet. And then sometimes there are some interesting stories. For example, there's an astronomer in Nova Scotia who has lens removed from his eye, and actually that now means that he can actually see a little bit more into the violet, a little bit more into the ultraviolet than you and I can. But in general, the limitations that we have as a human body are entirely consistent with the principles that the universe is following. Of course, part of technology and what we do with technology then is to try to sort of push the boundaries of that and to do that in a beneficial way.
And just like sometimes, like some animal can see more than what we can see. Mm-hmm. I think of that like they're seeing things that I can never see.
Yes.
And it just sometimes, if I obviously I don't go around and thinking like, I'm so frustrated because I can't. But like sometimes I think that it is so frustrating that some of the things I just can never, ever, ever do.
Yes, and of course they also would be feeling, if you were to anthropomorphize them, that they regret that you can do so many things that they cannot do. So I think there's always going to be a trade-off in any consistent schema. And science is and really the universe in which we live, it's a schema. So there is going to be a trade-off that necessarily happens with, you can do A, but you can't do B. If you could do B, then you might not be able to do A.
Yeah, I guess it's I should maybe change the perspective and think like, it is reassuring that everything is consistent and nothing freaky is going to happen out of nowhere.
I think that is certainly consistent with what that is what history sort of does show us, and it can, I think, and this is why I think physics and philosophy often are sort of they're bedfellows in a sense, is that I think it does it can give people some solace that there's, that we have the universe. We still don't understand all its rules or its principles, but it does operate in somewhat of in really a reliable way. I mean, one of the things we encounter in astronomy is, as you know, is that we can make predictions of the planets incredibly far into the future. I mean, the next time Venus is going to pass in front of the sun in what's called a transit of Venus, in a way that we actually observe Venus passing directly in front of the sun, is not for another 100 years, but it's happened to be known to be on something like December the 20th, in sort of 97 years' time. That type of prediction is quite remarkable. And thus far, predictions have proven to be correct. So we have no reason to think that one won't be. And fast forward 97 years or the precise day that it is. And it gives us as humans a degree of humility that perhaps we aren't the people setting the rules in the universe, but also a degree of confidence that we can then work within the principles that are set by the universe.
So there's one great video on YouTube that's called Map of Physics, and the person just laid out what different category of physics, that kind of thing. And then one thing he points out at the end is there are way more things that we don't know than we know, and there's one thing called dark matter that makes up 85% of the universe. So what we're doing right now is understanding the 15% of the universe. So this is another thing that I don't walk around thinking like we know so little. It's just sometimes when I'm by myself, can't fall asleep, I think like, we don't know a lot at all. There are way more we don't know than we do know. It's just does it frustrate you, or does it make you feel like?
So I think of it maybe to connect both to the different rooms that I discussed at the beginning. I find it beautifully rich, beautifully elegant, that there is so much that we don't know. But I recognize that one can have a view, well, gosh, there's so much we don't know, this is a problem. There's a wonderful talk by a neuroscientist by the name of Stuart Firestein from Columbia University, in which I think it's entitled "In Pursuit of Ignorance," and he was giving lectures to his first year biology students, concentrating on the brain, and he recognized that there was this perception that his students felt that basically scientists find out a piece of information, then they throw it into a textbook, and then it's taught to the students, and the next scientist finds out another piece of information, sticks it in the textbook gets bigger and bigger and bigger. In fact, I think he made the point that the textbook weighed as much as 2 human brains. Then he sort of developed a course to really convey that the more that you know, the less that you know, but that isn't a cause for concern. That's a cause really for empowerment, because behind every great advance in science is pursuing more and more ignorance, i.e. pursuing more questions that you can ask. So if you picture someone who has no training in a subject, they could ask, and you ask them to think of questions. Of course, they can think of a large number of questions, but if you then ask somebody who has training in a subject about that subject to think of questions, they will think of many, many innumerable more questions. So the search for an acceptance of ignorance is a crucial part, I think, of being a scholar, because the more that you find out about any topic, then the more interesting it is, because it's got so many more faces now, so many more areas of study that you can investigate. So, for example, you could say, okay, I'm sort of curious about how my eyeball works, and that's a perfectly good question to start with. And then you can say, okay, so what forms this eyeball? And you can sort of say, well, it's got this window at the front called the cornea, fine. It's got this thing called a lens, fine. It's got this retina at the back, okay. And then you start saying, well, so what's the cornea made of? And you'd say, well, it's made of the same stuff that your tendons are made of. And you'd say, but that's odd, because the tendons that I have in my body, and I've seen tendons when I go to the butcher's or whatever, and I can picture my Achilles tendon. I can't see through my Achilles tendon. So why is it that I can see through my cornea, this window in front of the eye, when I can't see through my Achilles tendon? I mean, and if I took my Achilles tendon and split it in half, it would still just look like wax paper. I couldn't see through it. And so, in essence, we've started by saying, okay, how does the eye work? And very quickly, we're in really quite an interesting question, which is, why is it that the collagen that makes up your eye, your cornea, and the collagen that makes up your tendon are so differently arranged in such a way that one of them lets this beautiful amount of light, as you said, from blue through to red, from red through to violet, if you like, through your eye, and any of your other tendons in your body doesn't do that at all. So that's just one question that probably you wouldn't have asked had you not even entered that subject to start with. So again, sort of playing the connection, the bedfellow connection between investigative science and the philosophical questions of humanity. I acknowledge that we could conclude, wow, there's so much we don't know, I'm kind of going to give up. I think it's both there's more solace and more utility in embracing that ignorance, and this talk by Stuart Firestein makes a good argument for this, and he indeed teaches a course on ignorance at Columbia. And so the art of the not knowing is as enthralling, as exciting, and as powerful as really any scholarly pursuit.
This is me when I'm editing this episode. After Rayf's response, it took me a few moments to digest it, and listening back, it sounded very awkward, so I'm just going to skip ahead to when I asked him the next question. Why do you like rowing?
Peace. I think it gives a remarkable sense of peace. It connects with many senses. So when you're rowing, you have often a stillness on the water, occasionally punctuated by hearing the oars sort of go into the water, and so it has a certain the water being wet question connects to the fact, I think, that we as humans have been, we're very familiar with water, and it provides fresh air, and so you have the sensory smell of being on a beautiful river or a canal, as we are here at Trent, and it's a pursuit of getting of improvement. In other words, it gives everybody is, every rower is essentially searching for that perfect stroke, and we never get that perfect stroke, and that's okay, because the journey is so satisfying itself. It gives tangible benefits as you improve. It becomes easier and easier to row. In that sense, perhaps it's similar to physics, that I think physics is probably most difficult at the high school level, because there's so much that you aren't able to connect the dots. It's a puzzle that you're very limited in placing pieces together. And as you become more accomplished in physics, it actually becomes easier to conduct that conduct that enterprise. And rowing, I think, is similar. That when you first get in a boat, it's very narrow. You fall to the left, it falls to the right, and it certainly isn't very comfortable. And after some time, whether it's the 10,000 hours that we hear about, or just a certain number of months of training, it becomes much more a pleasant experience. And so I think the reward comes with the pursuit.
Do you have a favorite scientist? You can name two if it's too hard for you.
So I suppose, there are of course many luminaries who I admire. I wouldn't say that I have heroes. I don't maybe think that a hero. There's a quote: "You should never meet your heroes," and I think part of science is, of course, taking the knowledge of that's gone before you and pushing it forward and continuing that discovery. And so that doesn't necessarily, and so I think a scientist needs to be open-minded to the extent that all the rules may change. We need to allow for rules changing, or the principles changing. And so in that sense, I would say that I have remarkable respect for many luminaries before me. I could name many of them, sort of in a word association test, perhaps. James Clerk Maxwell was a remarkable scientist who connected many areas of physics together. I would say that Newton was remarkable in just his ability to appreciate experiment as well as theory. I would say that Marie Curie was remarkable in just sort of determining radioactivity, and even Florence Nightingale was a statistician. Or I don't know if you're familiar with her. She's a nurse who worked a lot in the Crimean War, but was able to argue why it is that various hospitals needed to have improved sanitation, and did so in very much an experimental scientific way by presenting data in this way. So Newton used the line that he stands on the shoulders of giants. And I think there are many luminary giants that have gone before me, and they're all part of the team, and I think that's humbling, but remarkably able to be appreciated is the people that are part of the team.
Anything you want to talk about?
I could talk for hours, as you can tell. I think so. I'm sorry if I'm overstaying my welcome.
No, it's great.
So no, I mean, there's. I mean, I think that the pursuit of scholarship that comes from teaching and from research, asking questions is what I would encourage all students to do. I at the beginning of the interview, or just before the interview, you alluded to the fact that on my webpage I give a quote from Rabbi, who was a physicist in the early 20th century, who made the comment that his parents sent him to school and didn't say, "Hey, what did you learn at school today?" when he returned, but instead said, "Hey, what interesting question did you think of today?" And I think that's really the crux of much of human progress, is just asking questions, and that's why I appreciate the questions you've been putting to me in this interview.
Thank you. So that does it for this episode. Thank you very much, Rayf, for joining me today.
Thank you, Clayton.